Welcome to our lesson on section 3.3, the product and quotient rules. Let's start our lesson by listing the derivative rules and shortcuts we have learned so far. We have the power rule that the derivative of x to the n, so we have a variable in the base, a number in the exponent, that is nx to the n minus 1. We have a rule for exponentials that the derivative of a to the x is a to the x times the ln of a. And we have a special case of this rule for e to the x. d to the x, d dx of e to the x is e to the x times the ln of e, just applying this same rule where a is the value e. But this is a special case because the ln of e is 1. So we just say d dx of e to the x is e to the x. And then we also have some properties of derivatives that we have learned that the derivative of a sum or a difference is just the sum or the difference of the derivatives, and that the derivative of a constant times a function is just the constant times the derivative of the function. Notice that we did not write down the quote unquote obvious rules for the derivative of a product or a quotient of two functions. So how do we calculate d dx of f times g or d dx times f over g? This is what we're going to be exploring in today's lesson. So a conjecture, a very good guess might be that the derivative of f times g is the derivative of f times the derivative of g. It would be a very reasonable thing to think that this might be the case. So let's test it out. Let's test this conjecture using two functions that we know how to take the derivative of, x squared and x cubed. So I want to take d dx of x squared times x cubed. And I'm going to do it two different ways. I want to know, is it equal to the derivative of x squared times the derivative of x cubed? Okay, so I'm going to do it directly by taking the derivative of x to the fifth. And then I'm also going to see, is it the same thing if I take the derivative of each factor separately and then multiply them? Okay, so if I do x squared times x cubed first and take d dx of the product, because x squared times x cubed, multiplying like bases, we add the exponents and we get x to the fifth. And the derivative of x to the fifth, I'm going to apply the power rule where I bring the 5 down, copy the x, reduce the exponent by 1. Okay, so I've taken the derivative where I do the product first and then do the derivative. What if I do the derivative of each factor first and then multiply them? So the derivative of x squared is 2x, and the derivative of x cubed is 3x squared. And when I multiply those two derivatives, I get 6x cubed. So these are not the same. Okay, so the derivative of f times g does not equal the derivative of f times the derivative of g, sadly. Darn, right? Like that would have been so easy. It also turns out that a similar conjecture for the derivative of a quotient of two functions is also not true. The derivative of f over g does not equal the derivative of f divided by the derivative of g. So, in the absence of the confirmation of the easy rule, um, we have to use the limit definition of the derivative to try to find d dx of f times g. So remember the definition of the derivative, d dx of f of x times g of x is equal to the limit as h goes to 0 of. Now you plug x plus h into the function and then you subtract the function itself. So when I plug x plus h into the function f times g, it's going to be f of x plus h times g of x plus h. And then I'm going to subtract the function itself, f of x times g of x. And then we are all over h. Okay, I am going to do a real fancy trick here. There's no reason to that you might think of this on your own, having not seen this trick before. So just try to follow along. Um, it's not hard to understand. It's just would be hard to come up with if you've never seen it before. Okay, so my fancy trick is that I'm going to add 0. Okay, I'm going to add 0 to my function, and adding 0 doesn't change anything, so it should be allowed. Okay. So this is going to be the limit as h goes to 0 of f of x plus h times g of x plus h plus 0 minus f of x times g of x all over h. Okay. Haven't changed a thing except put in plus 0. Okay, so that does not change the value of anything. So now instead of 0, instead of using plus 0, I'm gonna represent 0 by adding and subtracting the same amount. Okay, subtracting and then adding it back in. Okay, so this is gonna become the limit as h approaches 0 of f of x plus h times g of x plus h. Okay, and then instead of adding 0, I'm going to subtract something and then add the same amount, because subtracting a thing and adding the same thing is the same as adding 0. So I'm going to add minus f of x times g of x plus h. And I know you're probably thinking, like, why? Why? And I'm just going to ask you to just suspend your disbelief for a few minutes and watch it all come out beautifully. Okay, so I've subtracted and added the same amount, and now I'm going to do the minus f of x times g of x all over h. Okay, and I'm just going to highlight this bit is the same thing as adding 0. So instead of doing plus 0, I'm subtracting and adding the same quantity to the expression. That's equivalent to adding 0. Okay, now, question is why? Why the heck did I do that? So I'm going to put some strategic parentheses in here around the first two terms and the second two terms. Okay. Um, because in the first two terms, they share a common factor, right? I have a g of x plus h and a g of x plus h. Both terms within the first set of orange parentheses have a g of x plus h in it. And in the second set of parentheses, both terms have an f of x in them. Mm. So I have 4 terms in my numerator here. I don't have the same factor in all 4 terms, but 2 of the terms have a common factor, and the second 2 terms have a common factor. So I used the orange parentheses to group them so that I can factor something out of each set of orange parentheses. Okay, so in my limit definition of the derivative, in the first set of orange parentheses, the common factor is g of x plus h. So I'm going to pull that out. And what's left is f of x plus h minus f of x. Okay, and then in my second set of orange parentheses, there's a common f of x in both terms. So I'm going to pull out the f of x. And what's left is g of x plus h minus g of x. Okay, and this is all over h. Okay, and I'm going to need a new slide. So I'm going to screenshot what I've got here and move to the next slide. Okay, you may be starting to see where the choices came from. Okay, why did I subtract and add f of x times g of x plus h? Why did I group them strategically the way I grouped them? So when I see f of x plus h minus f of x, what's jumping into my brain is that's almost the definition of the derivative of f, right? The definition of the derivative of f is f of x plus h minus f of x all over h. And oh, it is all over h, right? And here I have g of x plus h minus g of x over h. So I've got the derivative of f and the derivative of g showing up in here. So I am just going to break this into separate fractions. And let's see where we land after that. The limit as h goes to 0 of, I'm going to rewrite this as g of x plus h over 1 times f of x plus h minus f of x over h. And then, so that's my this part right here. I have g of x plus h over 1 times f of x plus h minus f of x over h. So if you multiplied these two fractions, you would have f of x plus h minus f of x times g of x plus h, which is what I've got up here, all over h, because when you multiply fractions, you multiply the numerators and the denominators. So my denominator is going to be h, like it is up here. And then I'm going to repeat this process for this term over here, where I'm going to have f of x over 1, and then g of x plus h minus g of x all over h. And now I can take the limit, right? Take the limit as h goes to 0. So g of x plus h, when h goes to 0, this term goes to g of x, right? When plugging in my h equals 0, this just becomes a g of x. This difference quotient is the definition of the derivative of f. So this is f prime of x. Okay. Then I have an f of x over 1, which is just f of x. And then what is in this factor, g of x plus h minus g of x over h, when you take the limit as h goes to 0, that's the definition of the derivative of g. So that's g prime of x. Okay, and that's it. That's the definition of, that's the formula for the derivative of a product f times g. So let's write it out. d dx of f times g equals, so this says g times f prime, but multiplication is commutative, right? So I'm going to write it as f prime times g, f prime g plus f g prime. So to summarize, the product and quotient rules for differentiable functions f and g. d dx of f of x times g of x is f prime g plus f g prime. That is the product rule. We just derived it using the definition of the derivative. You can do a very similar derivation to find the derivative of f over g. I'm not going to go through it in the video, but I think it would be a valuable exercise if you are interested. You can try to mimic what we did in the product rule derivation, but you will come out with f prime g minus f g prime all over g squared. Okay, so at the start of this lesson, we showed that the sort of quote unquote obvious rule, what we thought the rule should be for the derivative of f times g, did not hold. Let's make sure that this rule holds for that same example that we tested earlier. F of x will be x squared and g of x will be x cubed. And I want to make sure that the derivative of f times g does equal f prime g plus f g prime. Okay, so I'm going to use x squared as f and x cubed as g, make sure this works. So this is going to be d dx of x squared times x cubed. Does that equal f prime times g? So f prime is going to be 2x, g is x cubed, f is x squared, and g prime is 3x squared. So I'm going to work the left and work the right, make sure they come out the same. So d dx of x squared times x cubed. So I'm going to do the product first and then take the derivative, and I get x to the 5th. And the derivative of x to the 5th is 5x to the 4th. Okay, and then I'm going to simplify what I got when I did f prime g plus f g prime. Make sure I come out to 5x to the 4th. So 2x times x cubed is 2x to the 4th. And x squared times 3x squared is 3x to the fourth, and that comes out to 5x to the fourth. So those are the same. So my new rule that I have derived holds for this example that we tested earlier. Let's practice with the product rule by doing an example. Find the derivative of f of t, which is t cubed plus 3 to the t, times 5 to the t. So I'm going to call this first function f, the one in parentheses, and 5 to the t will be g. And remember that f prime, well, I'm not going to use f. I'm going to say d dt of t cubed times 3 to the t, sorry, plus 3 to the t, times 5 to the t is going to be f prime g plus f g prime. So f prime, that would be t cubed plus 3 to the t prime. So the derivative of the first times the second. So just 5 to the t, plain old without taking a derivative, plus f, which is t cubed plus 3 to the t, times the derivative of the second, which is 5 to the t prime. Okay, and then I'm going to take the derivatives, do the primes. So this is going to be 3t squared plus, I might need more room, 3t squared plus the derivative of 3 to the t would be 3 to the t times the ln of 3. So that is this derivative. And then I still have times 5 to the t plus t cubed plus 3 to the t. There's no derivative on that. It's just the function with no change. And then times the derivative of 5 to the t, which is 5 to the t times the ln of 5. Okay, let's practice the quotient rule. So I have q of x, which is x cubed plus 2 to the x over x plus 1. I'm going to call my numerator f and my denominator g. And remember that the derivative of f over g is f prime g minus f g prime over g squared. Okay, so f prime, that's the derivative of the numerator. That's going to be 3x squared plus 2 to the x times the ln of 2. That's my f prime. Okay. And I have to multiply that times g. So I'm going to put parentheses around the whole thing, and g is x plus 1. Then minus f times g prime. So the numerator is f, and I'm not going to change it. It's just plain old f, x cubed plus 2 to the x, and then I have to multiply that by g prime. That's the derivative of the denominator. In this case, that is just a 1. And this is all over g squared, g being the denominator, so x plus 1 squared. This is the first activity for the section 3.3 lesson. Pause the video at this point, work through these activity problems, then come back and watch the video to get the solutions. Okay, let's go ahead and work our way through these problems. We want to use the quotient rule to find the derivative of j of x. So remember, the derivative of a quotient is found by using the quotient rule. F prime g minus f g prime over g squared. So my numerator is f and my denominator is g. So this is going to be f prime. The derivative of x squared plus 3x is 2x plus 3. That's my f prime. And then times g, which is e to the x. So I don't change g at all. It's just the function itself. We're just copying it. Then minus f with no derivative, just plain old f, x squared plus 3x, times the derivative of g. And the derivative of e to the x is e to the x, all over g squared. So this is e to the x squared. This is fine. You can leave it like this. In fact, I encourage you to leave your derivatives unsimplified unless there's a reason to simplify it. Like if if you were trying to work on a problem that involved taking the derivative and setting it equal to zero, then you and solving, then you might simplify what you get. But if the question is just find the derivative, just do the rule and leave it. Okay, so now this is the same function, j of x. Instead of writing it as x squared plus 3x over e to the x, I've written it as x squared plus 3x times e to the negative x. We just brought that denominator up to the numerator, made the exponent pop negative. So I'm going to use the product rule this time to calculate this derivative. So j prime of x is going to be f prime g plus fg prime. F is going to be this function in parentheses, and g is going to be e to the negative x. So f prime is going to be 2x plus 3. G is e to the negative x plus f x squared plus 3x times g prime, which is negative e to the negative x. We calculated this derivative in our previous class. You can see those notes if you can't remember. Okay, so we're done. I told you you do not have to simplify derivatives, but the answer we got for j prime when we did the quotient rule and when we did the product rule for the same function look different. And that's because they are equivalent. They're algebraically equivalent. We could simplify one into the other. And in fact, um, I think on the next slide, I will show you why these are the same. Okay, here are our two versions of j prime of x. This one resulted from the quotient rule. This one resulted from the product rule. I want to show you that they're the same. So I'm going to work with the quotient and try to turn it into the product rule result. So I'm going to work with this one, simplify it into this one. So the question is, are these the same? They should be. So I am going to rewrite this as 2x plus 3 times e to the x minus x squared plus 3x times e to the x all over e to the 2x. And then I am going to break apart this singular fraction into the sum, or actually the difference, of two fractions that have the same denominator. I call this unadding fractions. It's a common technique. So I'm going to rewrite this where each term, I'm going to put the e to the 2x under each term of the numerator. So 2x plus 3 times e to the x over e to the 2x minus x squared plus 3x times e to the x over e to the 2x. And then I can simplify because when you divide like bases, you subtract the exponents. So I have e to the x over e to the 2x, subtract the exponents, and you get e to the negative x. So this is going to be 2x plus 3 times e to the negative x minus x squared plus 3x times e to the negative x, which is exactly this expression. So the negative sign here became a subtraction sign, but these are equivalent. Yes. The initial results looked different, but they were actually algebraically equivalent to each other. Compute the derivative of each function below using the product rule, the quotient rule, or both. X cubed over e to the x plus 1. So I'm going to treat my numerator as f and my denominator as g, and I'm going to apply the quotient rule. So the derivative of this function is going to be f prime. Remember, the derivative of a quotient is f prime g minus fg prime over g squared. Okay, so f prime, that's going to be 3x squared times g, which is e to the x plus 1, minus f, which is x cubed, times g prime, which is just e to the x all over the denominator, e to the x plus 1 squared. And again, unless you have some reason to, don't simplify. Just apply the rule and circle it. This one is a product. So what this function in parentheses we're going to call f, and this function that we're multiplying by we'll call g. And remember that the derivative of a product is f prime g plus f g prime. So in this case, we've got g prime of t. It's going to be the derivative of the first times the second plus the first times the derivative of the second. Okay, so f prime is 2t minus 7. So that's my f prime, and then just times my g, plain old g, plus f t squared minus 7t times g prime, and the derivative of 3 to the t is 3 to the t times the ln of 3. H of y equals the square root of y times 7 to the y plus y. I emphasize the word times because I'm going to use the product rule for this. So first, I'm going to rewrite this as y to the 1/2 times 7 to the y plus y. Because when I apply my product rule and I want to take the derivative of this, I would like to have it in power form so that I can use the power rule. So I'm going to let this first function be f and the second one be g, and h prime of y is going to be f prime g plus f g prime. So f prime is going to be 1/2 y to the negative 1/2, and then multiply by g, which is 7 to the y plus y, plus f, which is just y to the 1/2, times g prime. And the derivative of 7 to the y plus y is going to be 7 to the y times the ln of 7 plus 1. Okay, for this one, I want to find the derivative of k. It looks like a quotient, and it is a quotient. It's a function divided by a function. And I could use the quotient rule, and I will get the correct answer if I do that. But there is a much easier way to do this problem by breaking this quotient apart into the sum of two fractions. Okay, so I can divide that x squared into each term of the numerator. So this is x to the first over x squared plus 11. Instead of root x, let's call that x to the 1/2 because I know I'm going to be taking derivatives, and so I want to write it as a power. And that's also over x squared. So I unadded two fractions because when you add fractions with the same denominator, you just add the numerators and keep the denominator the same. So these two are the same. We very rarely go in this reverse direction. Usually you'd see something like this and go, oh, I know how to add these together, add the numerators and keep the denominator x squared. But we are breaking them apart so that we can simplify this into two easy to differentiate terms. Okay, when you divide like bases, you subtract the exponents. So this is going to become x to the negative 1 plus 1/2 minus 2 is negative 1/2. So x to the negative 1.5. And now I don't need to use the product rule or the quotient rule. This is just a power rule problem. I can just take the derivative of each term by using the power rule. So I bring the negative 1 down, I copy the x, I reduce the exponent by 1, and then I repeat for the next function. Oops, I forgot my 11 there. Okay. Negative 1/2 times 11 is negative 16.5. Copy the x, reduce the exponent by 1. And there's our k prime. Okay, before we get started on the next activity, I just want to do a quick explanation of how to handle product and quotient rule when the letters try to confuse you. Okay, so remember that the derivative of a product, f times g, is f prime g plus f g prime. Okay, so instead of using the letters f and g, it might be helpful to just think of it as the first and the second. So this would be derivative of the first times the second function plus f, which is the first function, times g prime, which is the derivative of the second function. So this is just another way to think of it instead of having to use letters because sometimes letters get repurposed and they can be confusing. So it's derivative of the first times the second plus the first times the derivative of the second. And we can do a similar thing with the quotient rule. So the quotient rule, remember, said that the derivative of f over g was f prime g minus f g prime all over g squared. And we can do a similar thing here that we did above, okay? Instead of calling f and g the first and the second, though, let's call them the numerator and the denominator, okay? So f is the numerator, g is the denominator. So f prime g is going to be the derivative of the numerator times g, which is the denominator, minus f, which is the numerator, times g prime, which is the derivative of the denominator, all over g squared, and g is the denominator, so this is the denominator squared. There's a little mnemonic that people use for this, for the quotient rule, which is low d high. They're using low to stand for denominator and high to stand for numerator. Low d high minus high d low over the square of what's below. Okay, and this just changed the order. Derivative of the numerator times the denominator. Multiplication is commutative. So to make the rhyme, they wrote low first. So they did low d high minus high d low over the square of what's below. But these are the same. Okay, it's time for the second activity for lesson 3.3. At this point, you should pause the video, work through these problems, and then come back and watch the video to get the solutions when you're done. Suppose that f, g, and h are unknown differentiable functions. Use the product and quotient rules to find the derivative of each function. So f over h. Okay, so the quotient rule says f prime g minus f g prime all over g squared, but I don't have a g in here. That can be confusing. So um, it can be helpful to use the low d high notation. So low d high, so that's going to be low is h. D high, that's the derivative of the numerator. Low D high minus high D low, that's the derivative of the denominator, all over the square of what's below, h squared. Okay, so now I've got a couple of product rules. G times h plus f times g. So the derivative here is going to be derivative of the first times the second plus the first times the derivative of the second. And then I have to do that for this product and this product. So first, derivative of the first times the second plus the first times the derivative of the second. Now I have a triple product. The way I'm going to treat this triple product is I am going to put some parentheses around f times g. Okay, and we're going to call that the first, and we're going to call h the second. Okay, so when I take this derivative, it's going to be the derivative of the first. So it's going to be d dx of f times g. That's the derivative of the first, times the second. I'm leaving those out for simplicity. Derivative of the first times the second plus the first times the derivative of the second. Okay, and then the derivative of f times g, that's a product rule. So I'm doing the product rule within the product rule here. So the derivative of f times g is f prime g plus f g prime, and that's all multiplied by h. And then I have plus f g h prime. And then I'm going to distribute this h, and I get f prime g h plus f g prime h plus f g h prime. Notice how the primes are moving. I'm trying to take, I'm just going to write it over here, trying to take f times g times h prime of the whole thing. Okay, and I ended up doing f prime times g times h. So you put the prime on the f for the first term. And then my next term is f times g primes times h. So you put the prime on the next factor in the next term. And then my last term is f times g times h prime. You put the prime on the last factor. F over g times h. So I'm going to do low d high minus high d low over the square of what's below. So my derivative is going to be low, which is g times h. So that's low times d high, which is f prime. That's low d high minus high, which is just f, times d low. So the derivative, I'm not gonna actually take the derivative right now. I'm just gonna write times the derivative of the low, or the denominator, g times h. Okay, and then that's all over the denominator squared, g times h squared. Okay, and then I'm just going to take this derivative that I didn't do yet. I'm just going to take that derivative and I'll be all done. So this is going to be g h f prime minus f times the derivative of g times h is going to be g prime h plus g h prime using the product rule, all over g h squared. And I could do some simplification. I could distribute my f, um, perhaps cancel some stuff. But like I said a few times before, if I didn't ask you to simplify it, don't bother. Let j of x equal e to the 2x. Use the product rule to find the derivative of j. So I'm going to have to rewrite e to the 2x as a product. And I could do that by writing it as e to the x times e to the x. Because when you're multiplying like bases, you add the exponents. X plus x is 2x. And so now I can apply the product rule to find j prime. So it's going to be f prime g. So f prime is e to the x, g is e to the x, plus fg prime, that's e to the x times e to the x. And that's it. So this becomes e to the 2x plus e to the 2x, which is 2e to the 2x. Now I'm going to use the product rule to find the derivative of e to the 3x in the same way. So I'm going to work on finding the derivative of e to the 3x. And I could rewrite that as e to the 2x times e to the x and apply the quotient rule. So it's going to be f prime. So it would be e to the 2x prime times g, e to the x, plus, so that's f prime g plus f g prime, like that. Now I'm going to take these derivatives where I just put primes. I'm going to take those derivatives. The derivative of e to the 2x I did on the previous slide. I know that derivative now is 2e to the 2x times e to the x plus e to the 2x times the derivative of e to the x is e to the x. Okay, so to simplify, 2e to the 2x times e to the x. Again, multiplying like bases, add the exponents. So this is 2e to the 3x plus e to the 2x times e to the x, which is e to the 3x. So this comes out to 3e to the 3x. We could conjecture, based on the results of A and B, that the derivative of e to the kx is k e to the kx, because the derivative of e to the 2x was 2e to the 2x, and the derivative of e to the 3x was 3e to the 3x. So this is our conjecture. The derivative of e to the kx would be k e to the kx. We could confirm this using another method where I could say, trying to confirm here, the derivative of e to the kx. I could rewrite that as the derivative of e to the k to the x. And then e to the k is playing the role of a in the exponential derivative formula, right? The derivative of a to the x is a to the x times the ln of a. So the derivative of e to the k to the x would be e to the k to the x, that's a to the x, times the ln of a, and a in this case is e to the k. Okay, well, e to the kx, e to the k to the x is e to the kx, because when you raise a power to a power, you multiply the exponents. And and ln of e to the k is just k. That's the definition of a logarithm. And so that becomes k e to the kx.